Okay, hi everybody.
Hello.
Hello. I'm the chair of this session entitled Fabrication II. There are 3 papers and all the presenters are ready. So for each paper, we have 15 minutes presentation plus 5 minutes question. Altogether 20 minutes per paper, which gives the schedule for the session. And so we can start right away. And I'm going to give the floor to Matt Bright for the first paper. So Matt, you are co-host, and so you can directly start and share your screen. That's the same for everybody. Okay.
Hopefully everybody can see my screen and hear me. Okay.
Yeah, that's right. That's good.
Cool. Yes. So just to begin, just to set some context, if we look at both man-made and natural structures, everywhere in nature, you can see structures that are knotted or entangled in various ways, or can be considered as such. And as it happens, mathematicians have been considering knots in the abstract for about 150 years. So it's a very natural question to ask, can we use some of the tools that have been developed mathematically in knot theory to investigate other kinds of entangled structure, to classify them, and to perhaps discover new ones. A very quick jog for those who haven't encountered this topic before, through some of the key concepts. In the abstract, classically, we consider knots as an embedding of one or more copies of the circle into 3-dimensional space. Typically, however, when you look at knots, when you study knots, you study diagrams of them, which are projections of these embeddings into 2 dimensions, such that the kind of key data of the embedding, which is mostly where a circular component crosses over itself or crosses over another circular component, are preserved. If we then give an orientation to these circles, then those crossing points themselves also have an orientation. And in the top middle area here, you can see how this works. Essentially, the orientation is given by how the overcrossing element rotates onto the undercrossing element at a crossing. If it rotates anti-clockwise, we say that is a positive crossing. If it rotates clockwise, we say it's a negative crossing. And on the right here, you can see a couple of examples of a single component knot here, a very simple one, the trefoil with with 3 negative crossings. And here you can see the Hopf link, which is just the simplest of 2 component knots, 2 circles winding through each other. When we talk about investigating such structures, we investigate them up to an equivalence relation, which is ambient isotopy. Informally, this means moving the circular components in such a way that they don't pass through themselves or each other, which amounts to deformations of the circle away from crossings, or 3 moves proved in the 1920s by Kurt Rademeister, hence they're known as the Rademeister moves, shown here below, which are also ambient isotopies, local ambient isotopies of an entangled structure. So how do we extend this to the concept of a textile? Well, the way that this is done is by considering textiles as knots in a torus. What we mean by this, we take an embedding of, so we can take it as infinite. As a textile, we can consider as an infinite collection of lines in a plane, in a thickened plane. We say thickened to give it to give the lines room to cross over and under each other. And then we say it's periodic in 2 directions, so it can be translated onto itself in 2 separate directions. And then what we do is, in a very sort of classic way, we take opposite edges of a unit cell, as it were, of the repeating pattern of the textile, and we identify them. And what we end up with is we go from an infinite collection of repeating lines in a plane, which is difficult to think about, to a finite collection of circles embedded in the torus. And again, as with knots, we look at these in diagrammatic terms, and we use a classic torus diagram, just a square with the opposite edges identified. And in this particular slide, we see an example of a single component, so a single circle winding in first in a longitudinal direction around the torus, crossing twice with positive crossings in the orientation that we discussed in the previous slide, and then winding in what we call a meridional direction around the torus, as given by this kind of intersection between these 2 identified parallel edges. But even then, we're interested in actually computing with these things, and it's quite hard to do computations on a diagram. So how you approach this instead is by kind of reducing that diagram to a string of symbols. And we do this, we extend an idea from knot theory called the Gauss Code, which involves tracing along each circular component of a knot and kind of listing the order in which one encounters crossings. Here we've got some extra data, which are the meridional and longitudinal windings. So for example, if we take this red component of the knot at the bottom, so this red circular component, we can see it winds meridionally, and we give that an orientation. It winds meridionally anti-clockwise around the torus. So we give an H symbol with a positive superscript. We hit a crossing labeled 1. The labeling is kind of arbitrary. We label them numerically. We then wind longitudinally around the torus, but this time clockwise. So we give a negative superscript. And then we hit an undercrossing, and we denote an undercrossing by its label with a superscript, and that superscript is simply the orientation of the crossing as given, as you would for classical knot theory. And then you can do the same for the second component here, and you end up with a symbol consisting of 2 words, which consist of characters from a particular set of characters. And this gives you all the data you would need to reconstruct the diagram. The challenge here is that you can then create an entirely valid code from these that contains all the right symbols in the right sort of order. But then when you try and reconstruct the diagram using this data, what you end up with is a point where you have to cross over, where a component has to cross over itself in a way that isn't given that isn't given as part of the code itself. And we call that a virtual crossing, and we say that if you have one of these virtual crossings, then the abstract code is not realizable, because obviously we're interested in patterns from which you can make textiles. We're also not particularly interested, obviously, in a practical sense, in textiles, in embeddings that would just fall apart. So we define here very formally, but also in an informal explanation, a kind of proper textile as one where you can't insert some ribbon in the plane, in the thickened plane, such that it doesn't intersect the textile component. And we can avoid some cases like this by ensuring that there is at least 1 meridional and 1 longitudinal winding, so 1 H and 1 B symbol. That would avoid the kind of highlighted situations here, unfortunately not the one on the right. So that, with all these definitions, we can say what we've got as the input data for the work we've done, which is a set of single word textile codes of a given complexity. We define the complexity here as the number of distinct symbols in the code. And that, as the complexity rises, the number of possible abstract codes rises very rapidly. But our algorithm, which is the central result of our paper, reduces this number by an order of magnitude. And then with further manipulations, we can get this down to show that we have just 32 realizable textiles, which are proper and which are distinct in the ambient isotopy sense we've discussed. The central idea of the realizability algorithm is to take the code and to create a graph out of it. You create this graph and then you trace out oriented cycles in the graph. The idea being that if you attach disks to these cycles, topological disks, then for because the graph effectively recreates the diagram, what you will assemble is a surface which is homeomorphic to a torus. And if you keep track of how many cycles there are in the graph in relation to how many vertices and how many edges, you can calculate that very simply with the Euler characteristic, which for an orientable surface, which we know it is because the cycles are consistently oriented, should be 0. That, as you can see in the diagram on the left. If you look at the diagram on the right, what happens when you get a virtual crossing is you get contradictions that are easy to spot as you build up the cycles. For example, you get something that isn't even a surface and certainly wouldn't assemble into a torus. Just very quickly, the graph is no more and no less than vertices placed at key points on the diagram itself. Which can be read off, these vertices can be read off fairly simply from an augmented version of the paragraph, which includes the meridional and longitudinal circles that are represented by the edge of the diagram. Edges are then simply adjacent symbols in these words. The idea then is that for each edge you create an oriented pair, which is simply a tracking along an edge, either with the orientation that is given in the notional diagram. That orientation is given simply by the forward cyclic order of the symbols in the word, or against it. And because in this augmented code, a symbol for each vertex appears twice, you'll get 4 oriented pairs beginning at each vertex. And then very simply, you develop in the algorithm a set of rules that are essentially turning left at any given vertex. So you know when you have an edge that ends at a vertex, the next one will start. It will be one of the 4 symbols that starts with that vertex symbol. And we can use the data of the orientation of the oriented pair symbol and the orientation of the vertex themselves in the code, so the superscripts of the vertices in the code, to uniquely select the correct next pair. So in that way, we can absolutely assign every single pair, every single oriented pair, in the way we've defined previously, to a cycle, and we can count those cycles up. You can then look, as I've said, for contradictions. For example, you should see no cycle containing an oriented pair which is moving forward along an edge and moving backwards along an edge at the same time. But in particular, once you've counted them all, the Euler number of a surface built in this way should be homeomorphic, should give 0 so that it's homeomorphic to a torus. So we can simply feed the code in, and it can do all of this. And all we are doing in all of these steps is reading along, sort of back and forth along the code. So this has a linear time complexity. So we can reduce the input set fairly quickly, albeit that the input set gets very large. There are some final computational manipulations we can take as well. You'll note that ordering, that labeling of vertices, labeling of crossings is fairly arbitrary. So these two textiles here are the same up to relabeling, but it is a relatively easy matter to look at these look at the codes and spot from the position of different crossing symbols that these are the same. So we can kind of group these and select a single representative. The Redomizer moves we discussed earlier, we can't reliably implement them just by looking at the code, but there are a few that we can that reduce the number of crossings. So we can actually remove crossings. We know that we can remove crossings if we see some fairly simple patterns in the code. The rest has to be done manually. This reduces things substantially to a fairly easy to handle number. At that point, we need to calculate a polynomial invariant, and that can only be calculated on diagrams. So the point is to get down to the point at which you're just handling diagrams. You've got few enough few enough codes that you can just look at them diagrammatically. And this is described in the paper. Exactly how this is calculated, but it's essentially to do with labeling arcs and creating a matrix using the arcs, the way that arcs are incident on particular crossings, and it's proved to be invariant up to some polynomial relationships, so that we can say firmly that if we calculate polynomials from this diagram and two polynomials are different, then these are not ambient isotopic. These are not ambient isotopic textiles. Very quickly, there's a labeling system which we describe in the paper. This is a brief run because we're coming to the end to kind of show you, for example, these symbolize, well, these are non-oriented diagrams for complexity 5 knots, so 5 distinct symbols with 3 crossings. If you can imagine each of these as 2 textiles, depending on whether you give one orientation or another to the circular component, and the polynomials calculated from them show that they are indeed distinct. Where we are at the moment, we'd like to look at multi-component textiles, so codes with more than one word in. We'd like to look at higher complexities. The problem is the input set gets very large, so we can either reduce it up front or start parallelizing things. This is a next step. We want to be able to eliminate all improper textiles, not just the 2 easy cases, directly from the code. And we're working on ways to do that. We have a conjecture about what that might mean for the way cycles appear in the graph. And we'd like to implement more complex randomized moves directly from the code. But this involves kind of proving that they arise from certain textile code patterns. So thank you very much, and I'm happy to take any questions. Hopefully that's kept me in 15 minutes.
Thanks very much, Matt. So are there any questions from the audience?
Mm-hmm. Topology of, so there's one in the chat about topology of rectangular tilings and being extended. So the tilings the tilings arise from the doubly periodic nature of the textile. So in essence, a triangular tiling would have a very different topology. It wouldn't, in essence, be a textile. Because it wouldn't be embeddable in a torus. So we could think of what that would mean in a triangular tiling, but that would be a different kind of structure. Hopefully that makes sense. From there's that table of numbers. Yes, the final number, those are all that is provably an enumeration of all possible textiles with the given crossing number and a single word. Yes. So we go through in some detail the steps taken to prove that this is the case. But yes, those are all possible proper textiles. Also considering different number of types of threads. So yes, as mentioned at the end, what we would like to do is move to multi-component. So different number of different types of threads would translate to more than one circular component in the torus. The challenge there is simply you end up generating very large numbers of abstract codes, and we're looking at ways to reduce the input set up front. But yes, we would like to extend there. Okay, thank you.
I have perhaps one final question regarding the fact that if you apply your approach to, I would say, a real textile where fibers would have different colors. In this case, I mean, the smallest pattern eventually could be extended to some larger area, taking into account colors. But what do you think that this would change in your approach in terms of complexity, description?
So if by different colors, so threads of different colors would be in real world textiles would be different, would be woven in different ways. So they would be represented as different circular components in the torus. So we could label them with colors, and that would be interesting, kind of selecting. So yeah, I mean there is an invariant, a coloration invariant for knots, and we could investigate that, sort of how many colors would be required in a diagram. But yes, multicolored textiles we could work with by simply adding, I guess, more data on the color of the thread. How that would extend the mathematics of it, I couldn't tell you without experimenting with it.
Yeah. Okay. Well, thanks very much, Matt.
No worries. Yes.
So now I'm going to give the floor to Stanford for the second paper. You are ready? So I give you the.
Thank you. Yes. Let me go share my screen.
Yeah. You
can and
then
I'll tell me if it's working. Do you see my screen?
Yes, we see your screen. That's good.
Perfect. Thank you very much. And thank you very much for the introduction. I'm going to present a work about a design tool for objects created by casting. So casting has been with humans for thousands of years. When casting, a cavity called the mold is filled with liquid or an expanding material, which then hardens. It is then removed, and the removed object is called the cast. This method can be used to produce statues, but also sweets. And in fact, a large amount of small manufactured goods are produced by making a mold and then casting something with plastic in that mold. Let's examine the sweets example from earlier a bit closer and consider this Lindt chocolate bunny. I'm going to show you a video of how it's produced, and I hope that'll work over Zoom. I tried it before and it worked, but if it doesn't, there is a YouTube thing below. So this is how the production process works. They have liquid chocolate that is poured into these silicone molds. And you can see there's lots of them being produced at once. Now the molds are closed, and then the chocolate is swirled around in the machine so that the chocolate coats the entire mold. The chocolate then hardens, and at the end, the cast, our chocolate bunny, is removed from the mold. This example of a chocolate bunny motivates the kinds of molds and casts that we want to produce. Specifically, they should be rigid. Rigid molds are a very important subsets of molds in general, and they're important because the manufacturing process using a rigid mold is much easier than using a potentially flexible mold. Of course, this restricts the possible design space and the shapes of molds that we can make. The mold should consist of 2 pieces only. This makes, first of all, assembly and disassembly easier. You can think about the robot that disassembles a 2-piece mold just as to go like this. And there's no sequence. The robot doesn't have to do motions in all kinds of directions. The most important reason, however, is that every 2-piece mold is suitable for use in massive parallel manufacturing, what we're calling multi-mold, and what you saw in the video earlier. With the molds consisting of more than 2 pieces, this multi-mold structure is difficult because you can't disassemble 50 molds at once. And additionally, we want the 2 pieces to be separated by a plane, which we call the cut plane. This is not strictly required by the manufacturing process, but it makes the mathematical modeling that we later use easier. There is a lot of previous work in this area of research, and let me show you some of it. Herholdt and colleagues seek to decompose a shape into multiple height fields to then construct a many-piece mold. Not multi-mold, many-piece. Still rigid though. Here, the more complicated the shape is, the more mold pieces are potentially needed. You can see in this one example that is shown here, a robot that disassembles this would need to know how to disassemble 4 separate pieces. Malamo et al. Designed cuts for flexible molds. Such flexible molds enable the creation of very complex shapes using only one mold piece that has been cut. But then again, these are more difficult to use in any kind of automated manufacturing. Nakashima et al. Create 2-piece rigid molds out of any shape. For complicated shapes, however, their casts have to be decomposed into many pieces, and then each of these single pieces is cast in a 2-piece rigid mold, and then everything is assembled at the end. We can see that for complicated shapes, there might be no way at all to create a 2-piece mold that correctly reproduces the shape. After all of these previous works use something that isn't a 2-piece rigid mold. So in such cases where we want a 2-piece rigid mold, we must be ready to significantly deform our input shape. And because of the need for large changes, our goal is to come up with a design tool and not just an approximation tool that helps the user to guide any model to a shape that is castable with a 2-piece rigid mold. Here you can see a little preview of the design tool. I'm going to explain all parts of it in more detail later. Let's dive into the components of the design tool now. Let's start with a simple question. When is a shape castable, mathematically speaking? Assume that we have a shape that is modeled by a triangle mesh, as well as a plane, and this is our cut plane. On each side of the plane, we have the removal direction. This is the direction in which we plan to remove the object from the mold. They don't need to be exact opposites, but if they are not exact opposites, the shape will be non-smooth along the cut plane, as you can see here on the right. The 2 removal directions are not an exact opposite, so there is a not a discontinuity. It's still continuous, but there's a non-smoothness along the cut plane. For 2-piece rigid molds separated by a cut plane, this process boils down to a very simple mathematical condition. For every face, it must hold that the normal of the face n dot producted with the removal direction d is greater or equal to 0. We call this the removability condition. If it is fulfilled, we can successfully remove the cast from the mold, as you can see here on the right. And if it is violated, the cast will collide with the mold during removal. This removability condition inspires the following simple castability energy. The energy is half the integral of the minimum of, on one side, the normal vector dotted with the removal direction at each point, and on the other side, 0. It is a continuous energy, and at every point that fulfills our removability condition, the integrand is 0. And at every point that violates it, it is the magnitude of this violation. We minimize this castability energy by looking at its gradients to find the optimal removal directions d. The approach of gradient-based deformation alone, however, does not work to deform shapes into a castable configuration. Consider this simple bar, and the removal directions are simply the normal to the cut plane, up and down. We want to deform it so it fulfills the removability condition. This is what happens to a simple bar if you simply use gradient descent optimization, which means at every point you look at the gradient of this energy and step in that direction. The bar is severely twisted out of shape in a way that destroys its character. This on the right is more what we want. The bar bends and retains kind of its local characteristics. And how we achieve this is by using a popular geometry processing method called ARAP, as rigid as possible. Basically, what we do is find the most rigid deformation that pushes the shape towards castability. And this is kind of local rigidity, because obviously a globally rigid transformation does not exist. Otherwise, the object would already be castable. It turns out that just doing one step of this ARAP is not enough. what we use is repeated ARAP deformations until the shape is castable. So this does not result in as rigid as possible deformation, but think of it as an as elastoplastic as possible deformation. You can see a bunny shape with repeated deformations until at the end it becomes castable. With these repeated ARAP deformations, certain parts of the shape can be distorted quite a bit. Look at the eyes of this goat, which have been deformed a lot by a repeated deformation. If there are parts of the shape that are extremely important to the user, for example, the eyes of this goat here, we can configure the ARAP deformation to preserve the eyes, and they will not be distorted as much. This is done simply by weighting certain parts of the object more during the optimization. Putting everything together, here we can see the design tool in action. The user starts and convinces themselves that the shape is not castable, no matter which cut plane or removal direction is chosen. Those are the red parts of the shape are the ones that would collide with the mold when removing. Now, the user decides to let the tool pick the optimal cut plane and now deforms the shape to be castable. The user is unhappy about the way that the tool deformed the horns and ears of the cow, even though it is castable, and decides to pin them, as well as some points on the body of the cow, to the cut plane during optimization. The tool then deforms the shape with these constraints to achieve a fabricable results, corresponding to the wishes of the designer, and the designer is done. Here are a few models that we produced with our design tool. In each of them, we explore the different design possibilities because there is no one correct solution. We took the fish model that you see on the left here and designed it to preserve the exact shape on the tail fin of its tail fin on the top right, or to preserve the exact shape of its side fins in the bottom right. Each of these cases corresponds to a different choice of cut plane in the end. It's a similar story with this hand here. On the top right, we put the cut plane horizontally through the hand, giving us one possible design. And on the bottom right, we put the cut plane through the hand vertically, giving us a different possible design. Now, we fabricated some of our results. What we do is we have a 3D printer, so we 3D printed molds and used a kind of hardening foam to cast a variety of shapes. It's like a 2-component foam. You mix them together, pour it into the mold, and close it quickly because it hardens very quickly. Here is a lion. On the left, you can see the input shape. On the middle, you can see a graphical rendering of the design that the designer achieved. And on the very right, you can see the object that we actually fabricated out of this hardening foam. You can see on the object, if you look very closely, this kind of ridging pattern. This is an artifact of our 3D printer. Because of the way 3D printers work, they print these layers. If those layers aren't very tiny, you're going to see ridges in the final 3D printed object. If you would use a higher quality fabrication method for the mold, these ridges would disappear. And here is the cow. In fact, it is the cow that we saw being designed in the video earlier. Again, on the left is the input. On the middle is a rendering of the design input. And on the very right is a fabricated result. Here's a very interesting shape, the so-called Stanford Armadillo. Again, on the left is the input, and on the middle, you can see the result of the design. Now, this is a very complex shape, and it has lots of parts that would collide with any sort of mold if you tried to cast the thing on the very left. On the middle, you can see there have been significant deformations of the shape. However, its local characteristics are all still preserved. It is undoubtedly the Stanford Armadillo, even though, as you see, the legs have been rotated, it's now standing upright, the arms are up, and the ears are slightly extended. So all of its local characteristics are preserved, but there is a large deformation in the shape needed to accommodate the two-piece casting method. And we also made a very special treat, kind of Stanford bunny that is made from gummy bear candy, Gummy Bunny. We did the same thing. We 3D printed a mold and then you boil this gummy liquid, pour it into the mold, close it, and wait for it to harden. In this specific case, I would not recommend that you eat this bunny because the substance that we use to coat the molds to make them non-porous is highly toxic. But if you're a food manufacturer, consider producing molds out of food-grade material. Thank you very much for your attention and for letting me present our simple tool to create two-piece rigid molds. And I'm happy to answer any questions that you might have.
I forgot to remove my microphone. You have already some questions in the chat.
Oh, I'm still sorry. I'm in my presentation view. I can't actually see the chat. Let me exit it and go look for the chat. I'm very sorry. It seems that if I'm sharing my screen, I can't actually look at my chat. Let me try to exit this.
Well, you can stop sharing.
Okay, now I see the chat.
Okay, you see the chat? I'll say that's fine.
Did you consider curved mold removal paths? I did not consider curved mold removal paths. It sounds interesting. However, the problem I see with curved mold removal, not problem, I'm not seeing them much. We looked at industrial fabrication, and they don't seem to use curved mold removal paths much. I wonder why. I wonder if it's a lack of fabrication tools, or it's because there's some kind of additional complexity introduced by these. Yes, the artist can control that. I didn't show that in my video. There is if you can shift click on certain regions, if you shift click and select the region, then it'll weight it. And then there's a slider where you can pick by how much you want to weigh it. And then those regions will, during the optimization, get an extra weight, which in practice means that their rigidity is more important than the rigidity of the other regions. So they will be distorted less. But it's a simple selection. And I missed a question that was asked earlier. Let me start with Gershon's question.
Gershon, yes.
I'm not sure why the restriction of a planar partition. That is correct. There is no reason to restrict this to a planar partition. We did this purely to make the mathematical modeling easier. It would be interesting in the future to look at not just planar cuts, but all kinds of shaped cuts. If you have a cut that isn't a plane, it doesn't, you can still have a two-piece rigid mold, and you can still put it in a multi-mold, even if the separating thing isn't a plane, but a more complicated shape. And can the cut plane be selected automatically to minimize deformation of the object? Yes, that is something we have implemented. The cut plane itself only has 3 degrees of freedom, right? Which is the normal vector and where it is on the z-axis, basically. So with only 3 degrees of freedom, it's very easy to run a global optimization. So that's what we do. There is a button that you press, and it finds the globally optimal position for that cut plane. Cool. Are there any more questions?
Well, I just have perhaps one final question regarding the landmarks you are using. The landmarks that are associated with your model you are using to modify the model. I mean, how these landmarks are defined? I mean, is it just user defined? Is it?
You mean the things that are selected and pinned to the plane?
Yeah.
Yes, those are user defined in order to kind of, it's almost like the user is deforming the shape, but the user is deforming the shape in a kind of constrained design tool that will let the user achieve exactly what they want. Because depending on which different parts you pin onto the cut plane, you will get different results. As I think I've shown with the fish thing, if you pin the tail fin onto the cut plane, the tail fin will straighten. The tail fin will straighten. And if you pin the side fins to the cut plane, the side fins will straighten. And you cannot, as they say, have your cake and eat it too. You have to deform one of these in order to make the shape castable.
Yeah, so these key points are somehow the handles in the ARAP deformation process.
Yes, and we don't, that is maybe interesting. We don't let the user pick any point to pick to the cut plane. We use a kind of, we use a previous work that decomposes every volumetric shape into like its most important salient points. And we only let the user pick from those salient points.
Okay. Yeah. If there is no more question, then okay. So I'll thank you very much for your presentation.
Thank you.
Now I'm going to give the floor to the third speaker, Vinayak Krishnamurthy. Vinayak?
Yeah, I'm just sharing.
Okay, so you have the hand for the presentation to share your screen, and you can go on.
All right. Can everybody see the presentation?
Yes, we see your screen. I think it's okay.
So thank you very much. I'm Vinayak Krishnamurthy, and today I'm going to share our work on generalized Abel tiles. So we are all from Texas A&M University, and this is sort of a collaboration with Dr. Ackelman, who's also present here today from the Department of Visualization. I'm from the Department of Mechanical Engineering, and another colleague of us, Courtney Starrett, also from the Department of Architecture. Essentially, our work started when we started thinking about the notion of topological interlocking. And the principle, so topological interlocking is a design principle which was sort of introduced first in the mechanics community, in the materials, mechanics of materials community in 2001 in a more formal sense. It has been around for a very long time. So the principle itself says that suppose you have a bunch of elements or blocks, right? Each of them has, all of them are of the same shape, and the shape is sort of special. And if they're arranged in a certain way, such that when you apply a peripheral constraint, which means that suppose you're seeing a bunch of shapes on the right-hand side. So suppose I took a rubber band and I just put the rubber band around this collection of shapes, then each of these shapes will actually hold their place, right? And that is purely by the virtue of their own geometry and their mutual arrangement with respect to each other. So that's the basic principle behind topological interlocking. And the perspective, at least from the mechanics community, was to say that this toughens the entire assembly by the process of fragmentation, right? So this in general is a very interesting principle that we wanted to make use of. But if we go all the way back to Joseph Abel or Sebastian Touchet back in the 1600s, late 1600s, we see that they kind of used these types of principles, topologically interlocking principles, in order to construct domes and other types of vaults. So here I'm showing you Abel's flat vault, and then Touchet's vault, which is shaped in the size of a dome on the right-hand side. Right, so these are all shapes or structures that have been built by combining individual tiles, so to speak, that are all topologically interlocking with respect to each other. Right, and in fact, if we look at Weller's work on stereotomy, we'll see that actually Joseph Abel had thought of several different variants of his original flat vaults, which also had curved shapes, which was later generalized by Touchet in his designs, right? So this is kind of the historical backdrop behind topological interlocking. When we go into mechanics, we see that there's again a whole bunch of work that people have done from different points of view. Most of it comes from structural materials or architected materials. And the idea here is that these kinds of blocks, when assembled together, can be at least 10 times more impact resistant than if you had a monolithic form, right, which is like a single block. Okay, and you will also notice that most of the shapes that have been explored in the mechanics domain are primarily based on Abel's and Touchet's idea. Okay, on the other side, if you look at architecture, again, there's been a lot of interesting work in architectural geometry, which sort of takes Abel's original ideas and then creates a whole new set of topologically interlocking structures, right? This is one of the recent works from the graphics community from Wang et al., published in SIGGRAPH 2019, or rather TOG 2019, which talked about how to construct architectural shapes using topologically interlocked tiles. So they had a very interesting piece of work where they came up with the idea of using polyhedral geometry and the slicing of polyhedra, and then applying conformal mapping given an envelope shape onto which you want to construct these topologically interlocked tiles. So our conceptual framework for this work actually builds upon this idea of topological interlocking and another second concept, that is of space filling shapes or space filling polyhedra. So the basic principle is space filling shapes are the shapes if you replicate them using affine transformations, you can actually fill the entire space in a watertight manner. Another term for it is spatial tessellations, right? So there is a lot of work on two-dimensional spatial tessellations going all the way to Georgi Voronoi, followed by Delaunay. All these were, people who were working on crystallography, and then they were also looking at crystal structures and trying to see how different shapes are actually filling space. So then, between 72 to 82, Goldberg actually cataloged a whole variety of space filling shapes, right? So till date, we know for a fact that there are 8 convex polyhedra that will fill space for you, right? So, and 5 of these polyhedra are actually regular, so they have regular faces. In fact, the fact is that most of the space filling convex polyhedra that are known are actually prisms, right? Or they are parallelohedras. So that's sort of a limited set of shapes that can actually fill space. And also note that these are not generally interlocking in nature, right? So some of these shapes may be, for example, a truncated octahedron is actually also interlocking in a 3-dimensional sense. Last year, we ourselves wrote a paper to SMI called Delaunay lofts that sort of took this idea of convex space filling shapes to construct a new type of non-convex space filling shapes. So these are called Delaunay lofts, and the basic idea was to apply a layer by layer Voronoi partitioning of 3-dimensional lines that have been arranged using the known 17 wallpaper symmetries. So as you can see in the videos, essentially what we do is that we have a bunch of lines arranged in a special manner, and for each intersection of that line cut through a plane, we compute the Voronoi tessellation and then we integrate it across the vertical axis. Now, we did not notice this at the time when we were working on this paper, but actually these shapes are also topologically interlocking, right? So that's kind of what gave us the idea for the current work of generalized Abel tiles. So essentially, our approach is based on this principle of Voronoi partitioning, but with higher dimensional size. So what I mean by that is, suppose we all know that if we have a set of points in space, we can apply Voronoi partitioning, and we'll be able to subdivide the space into a set of cells, where each cell at any point in a given cell is closest to its corresponding site. So the red dots are our sites, and then we get appropriate cells. So what we wanted to start with was that instead of points, if we have lines, and by the way, this is also not an entirely new concept. It has been explored previously in literature too, but not in a completely formal sense. So if we have a set of lines, then we can actually also do a Voronoi partition, and we'll get something like this. Now, if you look at this picture, you will see some kind of a similarity between Touché's shapes of the warts, right? At least from the top view. And this is a very interesting observation, but I want to mention here that the curves that you see in this figure are actually not circles. So Abel and Touché originally created their interlocks using circular arcs, but the shapes that you get here are actually parabolas. That's because if you consider this point right here and this line, essentially this curve is a parabola where this line is your directrix and this point is your focal point, right? So that's the segmentation of the two-dimensional domain that you get, okay? So our basic idea is essentially to choose a set of high dimensional sites. It could be lines, curves, or surfaces, right? Configure them based on certain types of symmetries. And we are using these symmetries, and I'll explain why. And then apply Voronoi partition, okay? So before I move ahead, here are some observations, right? If we compared most of the work that has happened in this area of topological interlocking, so you take architecture, mechanics, or graphics, you will see that there is a common symmetry that all these shapes actually share, okay? And that symmetry is essentially in visual correspondence with fabric weaves. So I'm sort of excited about today's session because we talked about textiles in the first talk. Matt showed us some really great stuff, and then Odin talked about molding and casting that I'll get to later. So this is my connection with Matt's earlier talk, right? If you specifically look at Abel and Touche, you will also see that there is a two-plane system where the weave lines of the fabric are perpendicular. So what I mean by that is, if you were to look at Abel's flat boards, okay, you can think of them as two different weave patterns on the top and bottom. Both of them, in this particular case, are plane woven symmetries, right? Now, on the top plane, I can apply this plane woven symmetry in a certain fashion, and then in the bottom plane, I can rotate each of the weave lines by a phase angle of 90 degrees. And that's kind of what you see on the rightmost figure in terms of Abel's boards. Okay. So based on this observation, our approach actually uses fabric weaves as a method for exploring the design space of topologically interlocked tiles, right? And the reason why we did this is because it simplifies the design process very easily. We have a lot of interesting weave patterns that were abstracted out by Grunbaum and Shepard, and essentially they studied isonemal fabrics where they could associate three very simple parameters in order to construct different types of weave symmetries. So it provides us a very nice parametric space for exploration of generalized Abel tiles too. So based on this notion of weaves, this is the idea behind our algorithm, right? So let's go back to our original example where we have a set of line segments, and these the line segments that I'm showing you are essentially corresponding to plane woven weaves, right? So suppose instead of lines, I took just the endpoints of the lines. So the yellow points, dots that you're seeing, are essentially the endpoints of the lines that you see in this previous slide. The reason why I'm doing this is because I want to be able to compute the Voronoi partitioning without going to an image-based approach. So we wanted to retain the object space methodology. So in order to do that, we sort of discretize the lines. So this is an example that shows a set of points which are endpoints to the lines that I showed in the previous slide. So if we compute the Voronoi diagram, you essentially get this Cairo pentagonal tiling. Now, if we take each endpoint of a given line and connect them together, we take a Boolean of the polygons, the Voronoi cells that we get something like this. So if we apply this throughout the entire structure, we actually end up getting a very interesting set of shapes, which in combination can actually be interlocking, but not yet, right? So again, if we take that line and discretize it even further, you will notice that we end up getting something similar to what Touche and Abel were trying to show us, okay? So based on this, we can generalize this beyond 2 dimensions and go to surfaces in space. So for example, suppose I have these two planes, both having the same weave symmetry, which are mapped at a 90-degree phase angle. We can actually take each corresponding weave line on the top and the bottom planes, and we can apply some kind of an interpolation. So in this example, I'm showing you an interpolation that creates a set of ribbons, right? So each of these ribbon is now our Voronoi site for the decomposition of this domain, right? And note that, and this is a conjecture, by the way, so it is this 90-degree phase angle between the top and the bottom planes that enables our interlocking. So essentially, you can discretize the space and you can combine all the layers and construct a tile in the following manner, okay? So based on this, we generated several different types of Voronoi partitions are based on different types of Voronoi sites. So this is an example with T-shaped sites. Essentially, we populate the fundamental domain, which is our block, with these T-shaped sites, and then we first apply discretization on a layer by layer basis, and then we combine each layer in order to construct our tiles. So this is one example of a tiled assembly. We also applied this to three-dimensional Voronoi partitioning. So in this particular case, suppose we work with V-shaped sites, right? And we again populate the fundamental domain. Then we can discretize each side in terms of points and apply three-dimensional partitioning to combine the cells and get our final shape of the tiles. Okay? So these are some of the shapes that we explored. So we explored different types of tile designs. We also explored different types of weave symmetries. So these are two examples from plane weaves. The top one is layer-wise computation based on plane woven, and the second one is the three-dimensional based on V-shaped sites. And these are two different examples on the basis of twill symmetries. Okay. Now, of course, the discretization actually has some effect in terms of what kind of smoothness you get between the shapes. So we experimented with the layer-wise approach with different types of sites using a very low number of sample points. And you'll see that some of these site designs actually give a reasonable smoothness, while some don't. And in terms of three-dimensional Voronoi decomposition, we observed that usually you get a smoother looking surface as you increase the number of samples progressively. Based on this, we did some physical evaluations. I'm sort of short on time, so I'll run through this. So we did some physical evaluation. We fabricated these tiles using 3D printing. We also did the fabrication using aluminum casting. And this is where I wanted to connect to Odin's earlier talk. Right? We thought that it will be very difficult, but actually it turned out to be reasonably easier for us to cast these using aluminum and wax. Perhaps he can take the shapes from us and make chocolate castings for this kind of stuff, right? We also did a finite element analysis. So we constructed three different types of assemblies using three different types of tiles, and we simulated using the following constraints. So we applied a peripheral fixing to each of these tiled assemblies, and we displaced each of the central tile by about 2 millimeters, and we observed the von Mises stress values. So these are the stress distribution patterns. You will see that there is some kind of a relationship between both the sites that were designed and also the weave symmetries that were allowed. When you compare it with a monolithic box, you see that there is an interesting set of patterns that emerge, and we are yet to discover what the what the geometry to the structural relationship is. When you compare it with Abel's original walls, what we realized was that Abel's walls are actually non-stable in the sense that if we marginally change the input parameters to the FEA simulation, you get very, very different types of results, and we didn't quite observe much symmetry in terms of the distribution of the stress. Okay, I'm also going to compare the different tiles. So the twill tiles actually experience the highest extremal stress, and that's probably because of the shape, the T shape that we use. We also had similarities between the plane woven tiles in terms of the average stresses, although they had quite dissimilar behavior in terms of the maximum stresses that they had. Right. So I would like to end the presentation with a brief discussion of the limitations. Of course, we applied it to 2.5D geometry, so we considered only flat domains. We would like to go to more curved domains, and we want to analyze the geometry to structure relationship. But we think that based on what Matt talked about today, there's a very good chance that we can generalize this idea by taking the notion of knots and links, and by mapping the different types of sites and weave patterns to the stress distributions. Lastly, we want to explore the notion of reciprocity, which goes all the way back to Leonardo in terms of his grid design, and see what new types of shapes emerge using our interlocking algorithm. So this is all I have. Thank you and stay safe. If you have any questions, please let me know. All right. So
you have already some question in the chat.
Right. So can you make this, so Matt is asking, can we make this process work for any fabric weave pattern? There are constraints on the type of patterns that we use. Okay, so that's a great question. I don't think that there is any restriction, primarily because as long as you maintain the topological continuity between the two different planes, even if you were to take curved lines on each plane, or even if you were to do non-linear interpolation between the two planes, it is definitely going to work. And part of the reason is because of the way in which the algorithm is designed, right? Voronoi actually gives you, by definition, it gives you a space-filling set of structures. The key question is whether they are going to interlock or not. So that will definitely depend on how we curve the geometries on the top and the bottom planes, right? So that's sort of what I feel at this point of time. Can you go slightly more into detail to describe the process used for aluminum casting? Right. So I'll just pull off the paper. There's an interesting set of figures, if I'm not wrong, that look at the aluminum casting. Let me. So actually, it's not there in this particular version. Okay, so essentially for aluminum casting, what we did was we first printed a single tile using a flexible resin. Okay, then we actually so in contrast to, so first we tried to break the piece apart and try to connect it together. Actually, that gave us a little bit of this, a good amount of discontinuity between the two shapes that we had gotten, and we had some challenge. Then we actually tried to cut off near to the top plane, and we realized that actually, if you break it off in a transversal fashion, you get a better result in terms of connecting the two blocks together. So we were actually able to, in fact, in one experiment, we were actually able to nearly build the entire shape in a single shot, right? And we did some wax, lost wax casting to achieve this result. Does that answer your question, Odin? Okay, so what are the loading conditions under which the stress distributions are shown? Okay, so that is actually an interesting question. You see, we did not apply a load in terms of a force, right? What we because these are all individual tiles, right, that were combined together just on the basis of our peripheral fixation. So what we did was we actually applied a displacement ANSYS. So we did this analysis in ANSYS. It allows you to actually apply displacement directly and then compute the stresses on the neighboring tiles. So that's what we did. We did not actually apply an explicit load to any of the tiles.
Okay. I don't know if there are some other questions. Perhaps just one complementary question regarding the finite element computation and the loading. I mean, how did you consider the boundary conditions between the various elements of your assembly? Because I guess the gap between the components can have a significant influence across the way the stresses are going to be distributed in the overall domain. So what was your hypothesis regarding these aspects?
Okay, so just to understand the question better, when you say gap, do you mean gap in terms of the size?
Well, the clearance that I mean, if you consider the cast aluminium, for example, I mean, then the dimension are not the theoretical dimension. So you have some clearances between all the components, which are going to influence the distribution of the loads into your assembly.
Ah, that's a beautiful question. Actually, so you're right. When you do casting, because of contraction, you will end up with some kind of a tolerance between the different shapes. We haven't done any formal analysis on this, but at least at least for our 3D printed and wax cast molds, or not wax cast, 3D printed and the aluminum cast molds, we did not find much of a gap between them. But if you have a tolerance that is higher than a certain amount, what is going to happen is that they're going to shift within their own location, right? So the notion of topological interlocking, I mean, one of the reasons why it is kind of not used currently in architectural design is because, yes, they lock together, but they are also feeble. Now, in our case, it kind of, because we are doing it in a 2.5D sense, we still did not get. So we tried out some basic physical experiments. We did not get too much of a shift between the blocks, right? So in that case, what will happen is that the stress is going to either localize along the z-axis, that is the vertical axis, because one of the tiles is going to move up and down. The left-right movement is actually constrained quite a bit because of the way the shapes are interacting at the boundary of any of the two tiles, right? This is a rather complex question, I think, which needs a lot of further exploration, both numerically as well as in a physical sense. But I think we need more physical experiments in order to actually answer this question.
But I mean, in the context of your finite element computation, I mean, how did you, I would say, mesh all the components and define the relative contact condition between the elements? Because this can, at least, I mean, if you are considering the theoretical dimension, I mean, this can influence significantly, however, the result of your finite element computation, depending on the mesh size you are using and the quality of your input model in any case.
Right. So in our finite element analysis, so the way we did it was we constructed the assembly of these tiles using a standard CAD modeling software, where we actually connected the features of each of the adjacent tiles together, right? So there is a plane-to-plane mating that allows you to actually guarantee that they are going to form the theoretical, boundary as ideal as possible, right? So the analysis is actually for a real ideal case. You're absolutely correct, right? There was too much, yeah. Okay. James also had a question: are these tiles especially useful for brittle materials to direct cracking? Yes, actually, that is what Estin and Diskin's work shows, that specifically for brittle materials, if you have a topological interlocking, then the resistance to impact increases, but it comes at a cost of static stability. So the static stability decreases, which is sort of connecting to what Jean was talking about, and we also had this experience when we were trying to look at the physical assembly of the tiles that we constructed. But yes, mainly for brittle materials, it's quite useful.
Okay.